This is a short video just to walk you through some software that we might use to look at the direction field for some online systems here. You'll see this is of the this is four differential equations of the form x prime equals ax plus by and y prime equals cx plus dy. Okay, so then the matrix A here is going to be a, b, c, d. And so looking at the homework from things like 7.5, we're going to be looking at plotting the solutions for those. And so this software will be useful for that. So for example, if we take a look at number 3 in the book, the matrix here is going to be 2 and a -1 here, and then 3, -2. This takes a little bit to change 3 and -2. Good. And so now the algorithm is computing the determinant and the trace. The trace, by the way, is the sum of the two diagonal elements. I don't know if everybody has run into that before. And so in this case, our eigenvalues are -1 and +1, and you can see the eigenvectors here. And so we can also plot them here. And so we can see how the eigenvectors kind of formulate the basis, if you will. It's not a basis in the linear algebra sense, but it's very similar to that for all the solutions. And so you can see that all the solutions, by the way, these arrows right here are not directions. Those are just directions in time, I should say. Those are just showing the eigenvectors, because the direction in time here is actually going towards the origin in both cases. So all the solutions here are moving like this towards this upper right hand corner here. So all of these solutions are heading up here, right? And solutions over here spin around. And similarly, if I had started a solution down here, it would spin around, and all of these solutions are heading this way. And so this kind of a graph is actually the graph of something called a saddle. And so we won't get real deep into those, but it's useful to see some of these pictures. And so similarly, we might take a look at number 15, for example, in 7.5. The matrix is 5, -1, 3, 1. And actually, in this case, you can also double check your arithmetic, right, for your eigenvalues and eigenvectors. 5 -1, 3, 1. Okay. So we have two eigenvalues, 2 and 4. Those are two eigenvectors. And so you can see what's happening there. And so in this case, it's asking, well, what happens if x of 0 starts at the vector 2, -1? So 2, -1. So if we started here, where would we go? Yeah, you can tell where we're heading. If we started here, we'd just be heading up in this direction, right? So we'd be heading, what is that, northwest? Oh, northeast. Don't know my east from my west. Okay. And so as t goes to infinity, then this is just going to grow without bound. Okay, and so that's how you might answer number 15. Is this starting value starts down here in the third or fourth quadrant, and the solution's running out towards positive infinity, the magnitude of the vector. Good. All right. You can take out the eigenvectors if you just want to see what the solution curves look like. Okay, so I encourage you to play around with that a little bit. Yeah, this is often the case. It's easy to visualize things in 2 dimensions, but it's, once you start getting into 3 dimensions and higher, it starts to get a little bit tougher. So for now, we'll just when we're plotting things, we'll just keep it in 2 dimensions, and the link to this program will be on our class website. Okay, see you later.